All right, so let's talk about energy balances. So first, let's consider a system, right, represented by a box here, which is closed and has some heat generating, and we have some shaft work, right? So this is moving, right? Shaft work, and also let's put a piston here, right? So this is work of expansion and contraction. So we could say that the energy accumulation in this closed system, obviously closed being the fact that there's no mass coming in or out, right? The energy accumulation is going to be equal to, so the energy accumulation inside here, our closed system, is going to be equal to the heat flow into and out, right? So that's represented by Q here. So the heat flow in, out of our system, right? Plus the work done either on the system or by the system, right? So work done on the system or by the system. Okay? And obviously, just for the sake of completion, let's just define a couple of things, right? So we said that a closed, you should see that, right? Yeah, there we go. Okay, so a closed system, meaning that there's no mass flowing in or out of the system, right? Also, let's define a couple of things. Let's say that capital U is the total energy of system. Internal, excuse me. Total, yeah. Things would be a little bit different if it wasn't total, right? So this is the internal energy of system, right? Now we also have kinetic energy, right? Which in this case, I'm going to define it using the gravitational constant. So we have mass times, which is mv squared, right? 1/2 mv squared. V, I'm going to use a little u here. Instead of capital U, this one's got a little tail. Divided by 2 times the gravitational constant, right? Then I'm also going to define the potential energy as well, normally it's just, mgh, right? But in this case, we're going to say it's mass times gravity times z in this case instead of h divided by gravitational constant. Okay? So the energy accumulation here on the left-hand side of this equation is going to be equal to, what I'm going to do here is pull out a mass. So we have m times the change of the internal, the kinetic, and the potential. So that's u plus, write it this way. Let's see, we factored out an m, right? So this is u squared over 2 times the gravitational constant plus the potential, which is just gravity times z over the gravitational constant, right? So that's going to be equal to the change in Q, right, the change in the heat, flow of the heat, that's dQ. And in this case, this is an extensive property, right? So it's just, it basically just has units of energy. Plus shaft work, change in shaft work, also extrinsic, plus our piston here, so this is the change of expansion and contraction, right? So what I can do here, if we're assuming that the mass here is constant, right, I can actually divide both sides by mass and get something like this. So we have the change of, right, so if I do, let's write this one right here, right, 1 over m, 1 over m, right, divide both sides by m, I get the change of internal plus basically the same thing, gravity times z over the gravitational constant, which is equal to, now in this case, it's not going to be extrinsic, it's going to be intrinsic, right? So we have d times q plus, well, the change of q plus change of shaft work plus change in expansion contraction, right? So we've converted from extrinsic to intrinsic, right? So these are now in energy per time. So this is basically for the closed system here. So this is our equation for the closed system, right? For actually both of these, right? So this for a closed system, right? This is our energy balance for the closed system. So what happens if we have an open system, right? Say we have mass flowing in and out, and mass flowing in and out. So let's rewrite this and get rid of this. Right. So now we have some mass flowing in here, right? We have some flow rate. Right, so this is m in, this is m out. Right, so we have flow in, flow out, right? So now this is a open system, right? So we have mass flowing in, you have mass flowing out. So now this is going to change our balance a little bit because we have to consider the flow rates, right? So for an open system, we have the rate of energy accumulation, right? It's going to be equal to the energy per, so the energy per mass of the fluid that's coming at the inlet, right? So that's right here. Energy per mass of fluid at the inlet times the mass flow rate, right? Flat mass flow rate that's flowing in, okay? And we subtract from that what's coming out, right? So we have the energy per mass of fluid at the outlet, right, times the mass flow rate out, okay, right? So we have the energy times the mass flow rate coming in, subtract from that the energy times the mass flow rate coming out, right, of the fluid coming in and the fluid coming out. Now we consider everything else. So we have the rate of heat flow into the system, right? So this is plus the rate of heat flow into or out of system, right? And then also we have to consider the work, right? So plus the work done on or by the system. Okay. Now this looks messy, but if we consider or assume the fact that the system is steady state in terms of mass, right? So what's coming in is equal to what's going out. We can assume that the rate of energy accumulation is 0, right? So that means the left-hand side of this equation actually becomes 0, right? And therefore, we get something that looks similar to the closed system, but so let's rewrite this now in terms of numbers instead of words. So we get 0 is going to be equal to the sum of the inlets, right? This is obviously the internal plus the right, so the kinetic plus the potential, right, so this G, Z, or GC, times the mass flow rate, right, this is for the inlet, times the mass flow rate in, right, this dot indicating that this is mass per time in. Subtract from that the outlet, right, so give myself some room here. Subtract from that the outlet, right, so we subtract from that the outlet, sum outlet of essentially the same thing, right, of U plus U squared over 2GC plus G times Z over GC out times the mass flow rate out, right, M dot out. Then we have to consider the heat and the work, right? So that's plus Q extrinsic, this is a rate, right, plus the shaft work, plus the work. Now this is different. We have to consider actually the work of the flow of the fluid here through our system, because that's actually going to do work on our, that's actually going to either add or subtract work from our system. All right. So now, because the fact that we can write the work generated by the flow of our fluid as the following, right? Work of the flow rate, right? This is obviously a rate. This is going to be equal to the sum of the inlets and outlets, right? So sum of the inlet of, in this case, we have pressure times volume, which is going in, right? Times the mass flow rate, obviously in. And then we subtract from that sum the outlet, right? We have work coming in and then we have work going out. So again, pressure times volume, out times the mass flow rate out, right? And so therefore, actually these brackets should be like this, right, and like this. So not summing the mass flow rate, right? So therefore, we can actually take this and plug this back into here, right? So let's do that. Make sure I have enough room here. Like I said, this gets long, but it is derivation, so they have a tendency to get really long. Anyway, so let's plug that in. Right? So we get here the fact that basically we get this, right? This doesn't change. So we have 0 is equal to sum of the inlets times, and I'm not even going to rewrite this just for the sake of saving room and time, inlet, right? Minus the outlets times the mass flow rate out, right? And then we have plus Q, right? That doesn't change. Plus the shaft work, that doesn't change. Now we have our flow rate, so then this comes in here. Plus the sum, actually, you know what, we do this different color so you can see it better. Plus the sum, basically just this, right? So this is the sum of inlets of the pressure times volume in times the mass flow rate in, right? And we subtract from that the outlets, right? Because it's leaving times pressure, volume, right? We're summing that, the outlets, times the mass flow rate out, right? And so basically what we can do is we can combine these inlets and outlets with this, right? We combine them together. And so we can sum, you know, the internal, the kinetic, and the potential with the pressure, you know, with this, right? So what we get is following. All right, I'll leave this here on the bottom, give myself some room here. So what we get is the following. All right, so what we get is the fact that 0, right? Left-hand side is still 0, obviously, because it's that steady state. It's going to be equal to the sum of the inlets, right? Now we, in this case, now we combine them, right? So we have the internal plus P times V, right? Pressure times volume. Then plus everything else, plus the kinetic, right? U squared over to G sub C, and then plus the potential, right, which is G over GC times Z. And then we, obviously we have the outlets, right? Outlet, right? U plus PV plus U squared over 2 GC plus the potential GZ over GC, right? Plus the heat, right? This is obviously extrinsic. Plus any shaft work. Okay? Now, because of the fact the enthalpy is defined as, right, enthalpy is going to be equal to U plus pressure times volume, we can rewrite this. I'm forgetting the mass flow rate somewhere. Right, there's a m dot out, and there's a m dot, right, times the mass flow rate in. Right, because we factor that out because this is kinetic, this is potential, right, which obviously both have a mass associated with that. Right, so since the enthalpy is equal to the internal energy plus the pressure times volume, what we can get is we can rewrite this as enthalpy, and we get something really nice, right? So we have, use black here, we have 0 is equal to sum of the inlets. Right now, in this case, we have the enthalpy, right, which is just internal plus pressure times volume, plus u squared over 2gc plus gz over gc, right, times the mass flow rate in plus the outlet times h plus u squared over 2gc plus gz over gc times the mass flow rate out plus q, still extrinsic, plus shaft work, still extrinsic, right? And so this is your open system energy balance, which is assuming the fact that this is steady state, right? So go to this. This also from here. All right, so this is obviously assuming that this system is steady state, right? So this is our open system energy balance, assuming steady state, right? That's it. So what happens if we have unsteady state? Basically, what happens is this right-hand side stays the same, right? But we have the fact that, right, the left-hand side obviously is 0. So what's the left-hand side? Well, the left-hand side ends up being, right, the change of mass, right, times internal plus the u squared over 2gc plus gz over gc, right? And then this is going to be equal to this left-hand side, excuse me, the right-hand side. So this is going to be equal to that. Right, so this for unsteady state system. Right. So for the unsteady state system, the left-hand side is not 0. For the open, obviously these are both open. For when you have steady state, which is going to be most, if not all, of your problems, the left-hand side will be 0. And now normally when you do problems with this, the first thing you'll do is write the open system, whether it's an open system or the closed system energy balance, assuming steady state for the open system. And since the fact that this is 0, the left-hand side 0, and most of the time you can cancel a whole bunch of stuff out and you get something that's really nice and you can solve usually for Q if you're looking for that, or the shaft work or something like that. So hopefully this helps. Hopefully this long sort of possibly a little confusing derivation helped, because it's easy to apply an energy balance or any equation in general without knowing where it comes from and just plugging and chugging. But I think to get a deeper understanding of what's going on, it's really helpful to see where these energy balances come from, so that in any system that you're given, you can just sort of draw your infamous little box here, and then just write what's coming in, subtract what's going out, obviously plus your initial state or whatever, what you had to start with inside, and cancel stuff out, and solve for some and get some really nice results. So thanks for watching, and hopefully this helped, obviously, and we will see you all in the next video.